Hello everyone. In this tutorial we will learn about how to perform investigation in about corrosion in pipeline systems using PDM Fluent ANSYS. So we will investigate these simple pipeline systems. The fluid that will be go through this pipe will be the mixture of water and sand. These two ends will be the input and the other end will be the output. As we all know that in Fluent ANSYS, we need to create the fluid model instead the solid model. SolidWorks is very useful software in modeling, so in this software we can also generate directly fluid model. It means extract fluid model from the solid model. Let's take a look. The first, how to extract the fluid model from the solid model. We do this. We get into the flow simulation. Load the software first, flow simulation, and here create leads. Leads is means the enclosures of our systems. So we choose this one. We choose this one. 3, and the other end will be 4. So it's okay. So now our system is closed. It means the limit or the barrier of our pipeline systems. And then choose this one, check geometry. Make sure that everything will be checked. It means you will extract the internal surface or internal volume of these systems and create a fluid body. Make sure everything is checked. It means you generate fluid model from everything, from whole parts. Press check, wait 100%, and this is the result. Yeah, this is the result. It's look great. It's more look complicated. So many steps here to here, also here to here. It's not look so good. This step like this will be create many mesh and so many different skewness mesh. It means more calculation and hard to find converge. So I guess I need to do something modification of this model. Okay, wait a minute. I will modify a little bit. Okay, so now I finished. I avoid to make this simulation is complicated, so I make everything smooth, look like this from here, so we can fully generate fluid volume. So the outer surface will be the inside surface of our pipe, because this is the fluid volume, right? So from here we make sure that we save first, and tools, ANSYS workbench. Wait a minute. Okay, the ANSYS is open. Wait until our geometry is fully loaded, and then we choose fluid flow fluent, drag and drop into geometry. It means we share the geometry into our work schematic, and then mesh, We choose mesh, edit, and we will enter the design modeler. Okay, wait. And okay, we got our model here. So first, we make sure the geometry is fully loaded. Is check, it means fully loaded, and geometry coordinate system is okay. Mesh. Let's try mesh. Mesh is maybe sizing is good. We will try to sizing the mesh. We apply overall of the body. About the size, we choose maybe 10. Let's guess first, and then because we can imagine that corrosion will be start occurs from the inside diameters. It means the outside diameters of the fluid volume. It means we need finer mass outside, even we don't need to so fine inside. So maybe inflation is look good. Let's try. We choose overall body, apply, and apply of inflation. I choose overall body, so we can select all body. So mesh, generate mesh. Okay, we are waiting for mesh. I hope this is will not take a long time. After this, we need to create a name selection to initialize which side is our input and output. Oh, this is looks so dense. Let's see from inside. Let's cut first. Let's see. Let's see. Very. It's not too good, but it's too coarse inside. Okay, we change. Maybe 20. I don't need to find. I need. I don't need fine mesh inside. I just need fine mesh outside. Generate mesh. Actually, if we apply hexagonal or hexahedron mesh, I mean hexahedron mesh, we will get better results usually. But because this shape is like a cylinder, so tetrahedron as the default will be sometimes better. We try. Now we're doing name selection. We choose face. We choose two face. This is will be the input, so we create name selection. We say this is will be input, and the other two will be the output. Output. Press OK. So geometry OK, mesh OK, name selection OK. Let's see. This two and this two is OK. So we can minimize. Now they say need to update, so we update. Okay, they say okay. So we enter the setup. This wizard asks us about this one, double precision. Double precision, if you choose this one, you check this one, it means the software will try the best to find the converge. Our result will be better, but it will take a longer time. The software will be automatically decrease or make our convert criteria will be smaller, it means better result. But in this case, maybe I will not check this one, leave it unchecked. And this one, serial. Okay, we choose serial. Okay, we getting into fluent interface. Wait a moment. Okay, we finish. Okay, we our model is okay. And the first in setup general. In here we choose steady instead transient. Transient will be take very long time to to simulate. And because our about gravity, because our pipelines consist of vertical, it means gravity will be take place, will be affected in here. So we set gravity in z, so will be minus 9.81 meter per second. Okay, next we jump to models. Energy, no heat transfer, so leave it blank, leave it off. And viscous, yeah, this is viscous, we need to change this one. We choose k epsilons with two equation, and k epsilons model we choose realizable, and near wall treatment you can choose one of this. But sometimes if you want to find faster converge, we choose this one. If you choose this one, scalable wall function, iteration will be more complicated than standard wall function, so it it will be take a longer time. So in this case we will try use this one. And the others, no radiation, no heat exchanger species, discrete phase. Because our case is about discrete phase model, it means the in this pipe combination or mixture of water and sand. So sand is represented as small particle. So in these steps we will define that small particle here. First, this is very important, this is the most important step in this investigation. So first check this one, and about max number of steps, make it bigger maybe, just guess, I don't know what does it mean. So physical models, this one, this is our case, so we must activate the erosion, and then we set the small particle from injection, create injection name, and this one is surface. This is means the small particle is come from the same surface as the fluid is where come from. So we choose input, and here this is the material of our small particle. You can choose which one you like depending on your case, but I think this one I find in internet that most of sands is consists of this material, so leave this one. Uniform, and about variable velocity, no, my my particle is come from perpendicular with the input surface, so inject. Okay, check this one. Okay, so we create injection. Okay, and materials, we need fluid, water fluid, so go to fluent database, find water liquid, copy, close, close, choose this one, and make sure in cell zone condition. Choose this is also water liquid. Okay. Boundary condition. This is also important about input. Define input as mass flow inlet. You can choose mass flow inlet or velocity inlet. If your known parameter as unit as like a weight over time, you choose this one, weight over time. So your mass flow rate in kilogram per second. But if you choose this one, your known parameter will be velocity magnitude, which is in meter per second. This depending on your parameters. So in this case, I will try to use this one. I will put it maybe 2 kilogram per second, and this is supersonic initial gauge pressures, Pascal. Pascal. 1 bar, maybe around 101,000. Okay, I put it 100,000. 100,000 Pascal, maybe around 1 bar or 1 atm. And direction, normal to boundary. The particle and the fluid is come from direct perpendicularly from the input surface. Okay, and output, set output as pressure outlet. So leave it 0, it means the output pressure gauge will be atmospheric pressures. So it's okay. Wall, don't forget wall set as wall. Okay, dynamic mesh. We check dynamic mesh because if we set this static mesh, this will be never find converge, I think. Okay, we try to dynamic mesh. Smoothing, don't choose this one. This sometimes is not too suitable. You choose this smoothing. Okay. Reference value, we compute from input. About solution, we choose simple. This one monitors. I think we don't need from about this case because we just want to know the rate of corrosion, only the rate of corrosion, so only one result, so we don't need to define this one. About solution initialization, you can choose hybrid or standard. You also can choose standard, but sometimes you need to ask you another parameter, so just choose hybrid and initialize. So the system will initialize your case. This message say that initialization is done, so we can run to the next steps. We check case first. Say done. It's okay. Number of iteration, we must set this number. This is our guesses. Actually, ANSYS will stop doing iteration and calculation if they find acceptable value, which is it acceptable respect to the limit. We choose maybe this one 1000 iteration, I guess 1000. Okay, let's start to calculate it. Okay, yes, calculating is start to Okay, I will write back after this calculation is finished. Okay, see, we get converged now. It says solution is converged. It means this value is reach the acceptable value. So this is done in 524 iterations. Maybe you can improve your iteration. You may be less than this one by change your mesh. Maybe you can improve by change your mesh type into hexahedron or hex dominant, or you can doing the other like a map face. Maybe it will better. Okay, let's see. The solution is converged, so we can see the result now. See the result graphic. So maybe contours. We want to see the rate of corrosion in the wall, only in the wall, because the wall is in contact with the inside or inner face of the pipe, right? So we choose contours, setup, and fill. We choose here. Choose discrete pace variable. Instead, this one. We choose this one, variable. DPM erosion rate. So the levels is okay. Press compute and display. Oh, it means we forget to choose the wall. Wall. See the wall. Display. Look at this. This is the result. Look at this. In here. Maybe where is this? This is high. Where are you? Oh, here. Here. Look at this. This is where the most of mm, corrosion is take place. Here in this fitting. Look at this. In here. So it works. Yeah. Here. This is about where are you? Wait. This is about 1.18 E over minus 25. It's very small, quite small, but you must worry in this side. This is the most critical place, here and here. So this is all about DPM, discrete pace model from me. Okay, goodbye.